This is an online learning (LMS) project. The task course is EE 301 Communication Systems. Whole material of this course is redacted then dubbed by an American English-speaking TTS, text-to-speech, software, and put into this slideshow with animations for students to easily follow and understand. Instructor, Dr. Ali Kara. Reference book, Communication Systems, Simon Haken, Michael Moher. Noise and analog modulation. Receiver model. Transmission model. Noise performance of modulation schemes. DSPSC. AM. FM. Preemphasis and emphasis. Radio link analysis with noise. Noise as a Gaussian random process. Here you see on the right the noise process itself, and on the left you see the histogram of that noise. As you can see, the histogram has the shape of a Gaussian random variable distribution. Here you see a clean signal and a noisy one. The noise we study in this course is generally additive white Gaussian noise, AWGN. As the name implies, it adds itself upon the signal, it is frequency insensitive, hence white, and it has a Gaussian distribution. Transmission link model with noise. Receiver noise, which is the noise generated by the receiver itself, is additive, white, Gaussian, AWGN. We denote the noise at the output of the bandpass filter as N of T. We will evaluate receiver performance under AWGN by comparing various analog modulation schemes under AWGN. This is a model of the actual communication link. Noise, baseband transmission. Signal-to-noise ratio. SNR, may depend on type of modulation and demodulation. Basis for comparison of various modulation/demodulation schemes are the same average power for modulated signals, the same average power of front-end receiver noise, W of T, in the message bandwidth, W, noise, bandpass transmission. The noise at the output of the bandpass filter narrowband noise can be written in in-phase quadrature form. Average noise power is N0 times Bt, which is equivalent to KT0 Bt. For any format of S of T, calculate the average power of S of T. Question: BP filtered white noise in two parts. Part 1. Consider passing a white noise process through a bandpass filter. PSD of white noise and filter amplitude response square are given as SW of F equals N naught over 2, and H, F, amplitude square, equals rectangle, F minus 100 kHz over 50 kHz plus rectangle, F plus 100 kHz over 50 kHz. Find the PSD in Part 1, and autocorrelation function of the filtered white noise in Part 2. Sketch both of them. Solution. Part 1. Following the previous slide, it is a straightforward solution. N of F equals multiplication of SW of F and amplitude squared H of F. Note that the figure is normalized to N naught, as N naught is a parameter dependent on physical conditions and can change from hardware to hardware. Question: Noise, bandpass transmission. Calculate the average noise power, N naught, of the systems with following parameters. A. Environment temperature, T, 0, equals 0 degrees. B. T, 0, equals 25 degrees. C. T, 0, equals 0 Kelvin. Solution. Average noise power, or noise spectral density, is calculated by the multiplication of the Boltzmann constant, K, with the environment temperature, in kelvins. Note that C is an imaginary case, where the environment temperature is taken as absolute zero, which cannot happen in our universe. In this extreme case, it is so cold that even the normally random and fast electrons are no longer moving, therefore, they create no noise. Noise-temperature relation is worthy to keep in mind in the design of communication systems. in some deep space communications. In order to reduce noise to the extremes, the cooling of the receiver on Earth's surface is pretty common. Performance metric. Performance metric of the receiver in terms of SNR is how it changes the SNR of the signal from its input to output. This is the performance ratio, SNR of output divided by the SNR of input. T can also be called figure of merit. The higher this ratio, the better the performance. Question: performance metric. SNR, C, is defined as the channel's signal-to-noise ratio, whereas SNR, O, is the SNR at the output of the receiver. A system's noise performance, figure of merit, is evaluated by the ratio of its input SNR and output SNR. Evaluate the following expressions. Find the output SNR. Figure of merit equals 2. SNR, C, equals 10. Figure of merit equals 3 decibels. SNR, C, equals 12 dB. Figure of merit equals minus 6 dB. SNR, C, equals 12 dB. Solution: A, SNR, O, equals 20 B. SNR, O, equals 15 decibels. C, SNR, O, equals 6 decibels. Comment: note that A and B are good systems because they increase the SNR, but C is a bad system because it lowers the SNR. Noise performance of double sideband suppressed carrier in 2 parts. Part 1. In this slide we will investigate the noise performance of the coherent DSPSC modulation scheme. The received signal ST is comprised of a carrier wave, the message signal, and the system scaling factor, C, which has no significance in this calculations. The power of the received signal ST is calculated as C square A C square P over 2, where P is the message signal power, which is calculated by taking the integral of the spectrum of Sm of F over the message bandwidth, noise power, with a spectral density of N naught over 2, is found to be W, N naught, with a message bandwidth of W. Then the SNR at the input of the bandpass filter is found by dividing P, S, signal power to the P, noise power, noise performance of double sideband suppressed carrier, in 2 parts. Part 2. The noise added input signal is bandpass filtered, and the output is X of T, which has the received signal, ST, and in phase and quadrature noise components in it. This bandpass signal is then passed through a product modulator run by a local oscillator at the same frequency and phase as the carrier signal. The output of the product modulator is 2 low-pass and 2 high-pass components, which will be eliminated at the low-pass filter. As we eliminate the high-frequency components, we are left with the message signal MT and the in-phase noise component. At this stage we will calculate the signal-to-noise ratio and compare it to the one found in the previous slide. SNR of the signal YT is found to be C square A C square P over 2 W N naught. We call it output SNR. SNR output is equal to SNR input, therefore the figure of merit of DSPSC is unity, noise performance of an AM receiver in 2 parts. Part 1. In this slide we will investigate the noise performance of the amplitude modulation scheme. The received signal ST is comprised of a carrier wave plus the modulated message signal. The power of the received signal ST is calculated as A C square, in parenthesis, 1 plus K A square P over 2. Noise power with a spectral density of n naught over 2 is found to be W n naught with a message bandwidth of W. Then the SNR at the input of the bandpass filter is found by dividing P S signal power to the P noise power, noise performance of an AM receiver in two parts. Part 2. The noise added input signal is bandpass filtered, and the output is X of T, which has the received signal S, T, and in phase and quadrature noise components in it. This bandpass signal is then passed through an envelope detector. In this stage it is crucial to note that, in order to simplify the SNR calculations of the output of the envelope detector, we have the following two assumptions. Firstly, the average noise power is small compared to the average carrier power at the envelope detector input, and, secondly, the amplitude sensitivity Ka is adjusted for a percentage modulation of less than or equal to 100%. Then we can write the approximate Yt as AC plus AC times Ka times Mt plus the in-phase noise component. AC term is a DC term which has no meaning about the message signal, therefore it can be blocked easily, and we can ignore it. SNR of the signal Yt is found to be AC square Ka square P over 2 W n naught. We call it output SNR. The ratio of SNR output to the SNR input is then Ka square P over 1 plus Ka square P. Note that this entity is always smaller than unity, therefore in terms of noise performance, AM is always inferior to the DSBSC, which has unity ratio always. Question: noise performance of AM receiver. Find the figure of merit for an AM receiver, where the amplitude sensitivity Ka equals √0.5 and average power P is 1 watt for the system. Calculate the required channel SNR for an output SNR of 20 decibels. Example 6.1 Singletone modulation. Considering the singletone modulation, AM system must transmit 3 times more power to achieve the same performance of DSB if all other parameters are fixed. Ka is equal to mu, which is equal to 1, meaning 100% modulation. Question: AM versus DSBSC comparison. In DSBSC, regardless of your modulation parameters, the figure of merit is always unity. In contrary, in AM, it is determined by the modulation factor, mu. For a modulation factor of 80% in AM, how much more power should we use to get the same performance with DSBSC? Noise performance, FM receiver. Performance of the FM receiver is denoted by 3kF square, P, over W square. For the derivation of this figure of merit for the FM, please refer to your textbook's relevant section. Question: noise performance of FM receiver. Find the figure of merit for an FM receiver, where the frequency sensitivity Kf equals 25 kHz, average power P is 1 watt, and message signal bandwidth W is 25 kHz for the system. Calculate the required channel SNR for an output SNR of 20 decibels. Recall from previous lectures that delta F is equal to Kf times AM, which is equal to Kf times root P. Deviation ratio, D, was defined as delta F over message signal bandwidth FM, or W, from the figure of merit equation. It is easy to see that figure of merit is equal to 3 times D, Square. Satellite transmission system. We shall investigate the satellite transmission system as an example on how to work with input and output SNR requirements. First, let us investigate the system itself in its most simple form. The shown figure where two Earth stations are communicating via satellite is a relay system. Today some of the long-distance communications such as internet or telephone are done this way. The block diagram of the communication system in the satellite is given here. The incoming signal is passed through a bandpass filter to separate the received signal from among the different radio channels. Then, the low noise amplifier amplifies the weak signal in order to make it easy to work on for the rest of the system. Frequency down converter translates the frequency of the received signal to the desired downlink frequency. The traveling wave tube amplifier amplifies the signal with a high gain to make it eligible for sending a long distance to Earth. Note that this is somewhat an old system. Today's newer satellites incorporates digital signal processing in order to better relay the incoming signal. Also, the traveling wave tube is replaced by solid-state amplifiers. Revisit path loss and freeze equation. It defines the free space loss as a function of antenna gains and distance. PR is equal to PD, GD, GR, over LP, where propagation path loss LP is square of 4 pi r over lambda. R is the distance and lambda is the wavelength. The freeze equation is the fundamental link budget equation. EIRP is equal to PD times GD. EIRP is an acronym for effective transmitted power relative to an isotropic radiator in dB. Puerto Rico in dBW is equal to PD dBW plus GD dB plus GR dB minus LP dB. Satellite transmission system link budget. In order to visualize the link budget of the satellite transmission system, let's have a look at the figure. The transmitted power at the Earth station is Pt. This Pt is amplified by an amount of Gt, the transmitting antenna gain. Then the signal endures path loss, shown by Lp. At the receiver side, its power is Pr. This weak Pr signal is amplified by the received antenna by an amount of Gr. The antenna gains are typically high for dish antennas. Therefore, in power-sensitive applications, they are preferred, such as satellites. Question: revisit path loss and freeze equation. Calculate the received power, Pr, in a system with the following parameters. Transmit power, Pt, 1 watt, transmit and receive gain, Gt, equals 100, and Gr equals 1000. Distance between transmitter and receiver, R, equals 10 kilometers. Carrier frequency, Fc, equals 10 GHz. Receiver noise. Consider in link analysis. Thermal noise at the receiver is N0, which is equal to K times TE in dBW over Hc, where TE is the equivalent noise temperature of the receiver. K is 1.38 times 10 to the power minus 23 joule over Kelvin. When you add the noise figure of the receiver, the total receiver noise power for a bandwidth B is given by N, which is equal to FKT0, B, where F is the noise figure. Let us define the carrier-to-noise ratio. CNR is equal to received power over the noise at the receiver. To make it explicit, in dB form, the CNR is equal to transmit power plus transmit gain plus receive gain minus path loss minus thermal noise at the receiver. Question: receiver noise. Consider in link analysis. Each receiver has a noise figure, F, which is used to calculate the equivalent temperature, Te, by Te equals F times T0. Calculate the noise spectral density, N, naught, of the following setups. Question: Link analysis. Consider a communication link with the following parameters. Transmit power, P, T, 1 watt, transmit and receive gain, G, T, equals 100, and G, R, equals 1000. Distance between transmitter and receiver, R, equals 10 kilometers. Carrier frequency, F, C, equals 10 gigahertz. Equivalent temperature, T, E, equals 351.78 kelvins. Find the carrier-to-noise ratio, C over N, naught, and check whether the FM receiver with following parameters will work if it requires a received SNR of 70 decibels. Frequency sensitivity, K, F, equals 25 kHz per volt, and message signal bandwidth, W, is 25 kHz. Solution: the parameters are taken exactly from some previous questions in this presentation. So, find and then make the necessary calculations. Example: satellite link. Consider this example in following 2 pages on how to calculate different parameters under certain circumstances. Example: satellite link. Use the parameters from the previous slide and apply what we have learned in this lesson to get to the link budget of a typical satellite link. Question: Example: satellite link. Assume a carrier-to-noise ratio, 100 dB over Hertz, deviation ratio T, assuming this system uses FM as 1, and a message signal bandwidth, W, 100 kHz. Find the signal-to-noise ratio of this system.